Well, just had a bit of a last-minute dramas with the technology, as you do sometimes. And yeah, I've been rushing around pressing buttons, rebooting things, and so I'm all in a bit of a flap. Yeah. But anyway, I'm here and I've got a program for you, and it's all about overcurrent protection. Yeah. Your favourite topic. Yeah, maybe not. Okay, so what have we got up for today? So just a bit of a roundup of things. So for me, there's been a big week. Well, actually, the week before last, I was in South Africa, and it was an amazing trip. I went there as a guest of Herald's. Herald's Group is I think they're the biggest distributor of solar battery systems in South Africa. They service surrounding countries. 10 huge branches, really impressive business. And it was their founder, Hein Herald. He invited me over, and I ran some workshops, one in Johannesburg and one in Cape Town. And we did a bit of filming of some of their installations, which, one big one, I should say, which I'll show you in a tick. So that was a pretty exciting trip. First time to South Africa, bit of a learning experience. Some of the strange words they have for things. Hot tip, if they say, watch out, the robots aren't working, they're not talking about that sort of robot. They're talking about traffic lights. That's right. Traffic lights are called robots. Yeah. And if they say you've got a geyser in your cupboard, it's not an old man, it's a hot water tank. The geyser is a hot water tank. I love those little wacky turns of phrase. I mean, of course, every nation has them. I'm from New Zealand. We wear jandals on our feet. If you wonder what those are, some people call them thongs in Australia, but of course that's underwear in the UK. So, isn't the world a strange place when it comes to local terms? So, welcome back, everyone. I had to skip a week. As I said, I was in South Africa and I couldn't do my Toolbox Tech Talk, but it's all good. Just a reminder for those, I know I plug it every show, but really the Smart Energy Council are doing a great favour for the industry, particularly solar installers, by offering their Smart Installer program. And now it's $99 if you want to get access to a bundle of 9 Australian and New Zealand standards. I mean, that's probably worth thousands, and you get it for $99, so that's fantastic. You also have access to over 170 CPD points and links to great content like me. I'm on there too. So yeah, that's it. And just a reminder that there's a whole bunch of roadshows running. The Smart Energy Installer Roadshow. So the Smart Installer Roadshow, Canberra, starting in February 11, or we just missed that one. Brisbane, February 13, we missed that one. Melbourne, February 18, that's the next one up, sorry. And Adelaide on February 20. Those are the Smart Installer Roadshow. And Solar Cutters have you covered as well. So big shout out to Solar Cutters for supporting this program. And they've got roadshows ranging from Bendigo, Hobart, Penrith, Melbourne, Cairns, Newcastle, Byron Bay, Adelaide, Geelong, Canberra. They're not going to South Africa. Townsville, Perth, Brisbane, and Albury. So yeah, lots of training opportunities out there through the Smart Installer roadshows and the Solar Cutters roadshows. Don't forget, the big event for the year is the Smart Energy Expo 9th and 10th of April here in Melbourne. Sydney, there in Sydney. There is, of course, the other event back in October, I think, or it'll be on 29th and 30th of October, which is All Energy, and that one is in Melbourne. So those are the two big expos and conferences for our solar industry here in Australia. So without further ado, let's get into it. And just checking, oh my gosh, my stream bit rate is a bit low. I've actually had a little tech problem with one of my connections to the internet, so I'm on my backup connection. So if it's stuttering a bit, I apologise. The stream will be available afterwards without buffering. So if you just get sick of watching it, it will be available as a pre-record. So sorry about that. I'll have to sort out that tech glitch before the next Toolbox Tech Talk. So let's get into it. What are we talking about today? We're talking about string overcurrent protection. And I'm going to run through some slides with you that I've made from excerpts from 5033, and also compare the international standard as well. So the international standard for PV arrays, which is IEC 60364-7-712. Whew, that's a bit of a mouthful, isn't it? It's actually based on the Australian standard. Amazing. The Australian New Zealand standard 5033, first published, I think it was 2005, was largely adopted by the IEC. It's really because we were the first ones out of the gate with a national PV standard, and it informed the IEC, and we've been represented on that committee. At the time it was Professor Ted Spooner, a legend to those who know him, and had a big impact on the writing of the IEC standard for photovoltaic arrays for requirements for special installations or locations of solar photovoltaic power supply systems. That's the full name of the IEC standard. There you go. So let's have a little look at the first clause here. So what I'm talking about, string over current protection. Do you need it? Where do you need it? Why do you need it? Of course, I better explain this using my favourite methodology, which is my little overhead camera with a bit of drawing action going on. So let's just get that happening. So there we go. That's the overhead. Right, and if you hear some little tinkly sounds in the back, it's pouring with rain here. Melbourne, they say 4 seasons in one day. Well, we've sort of had 4 seasons in a few days. It was stoking hot a week ago, and now it's 10 degrees and raining. All we need is snow, and it'll be the complete picture. So let's have a little look at this scenario here. Now, first, a few definitions of terms, and we'll start with PCE, power conversion equipment. I mean, an inverter is power conversion equipment. Anything that converts voltage, frequency, or current is power conversion equipment. But most likely, this will be an inverter or a charge controller, something that charges a battery system. But I'm going to focus on it being an inverter. Keep the batteries out of this equation because they add another level of complexity. So when it comes to string over current protection, when do you need it? Well, when you've got one string, you don't need it because there's only one string. And some people say, well, isn't it better just to put a fuse in there anyway? Because, it's going to protect things. It's going to make sure that nothing bad happens. Well, it will be A, a nuisance, and B, do nothing. And the reason for that is that the fault current from a PV module is only a few percent higher than its operating current. So you just don't have enough discrimination for a prospective fault current to clear a fuse or a circuit breaker. So there is no purpose in putting any overcurrent protection in a single string. But once you start paralleling strings, you've got parallel sources. And under certain conditions, that parallel source can be a fault current to another string. So let's make a little scenario here. We've had a big lightning storm and some hail, and it smashed the panels, and so we've got a fault to earth here and onto the rails, and we've also got a fault over here. Now you actually need 2 faults in a floating system. That's because you need a path. So now we have the ability for this string to backfeed this all the way around and up here and up here. So we've now got circulating currents within our PV array. By the way, there's no chat happening on here. I just wondered if anyone's actually watching. I kind of like to know there's a few people out there. Say hi. And okay, so I'm getting a little error message about the streaming quality. It's probably because of the rain, and I'm on Starlink because that's my backup when I'm streaming. But anyway, I'll press on because I know this is being recorded locally, and I'll be able to share it with you as soon as this live finishes. So where we've got this fault current flowing around in the system here, we have to protect the modules from thermal damage and all the cable systems as well. So what is the potential for thermal damage to a PV module? That's what's known as the series fuse rating. So I've just pulled up here some Jinko Tiger Neos. These are actually bifacial modules. We'll get onto the bifacial problem in a bit, but let's say these panels are just parallel to the roof. No bifaciality at all, and they've got a short circuit current of 15.8 amps. So that means I've got 15.85 amps here flowing into a parallel string. And that parallel string is capable, and that's what the series fuse rating represents, of withstanding up to 35 amps. So as long as this number is less than 35 amps, no requirement for string overcurrent protection. Now remember, all bets are off if you've got other sources. So if you've got batteries connected or DC storage on the PV array, then you've got to consider those fault currents as well. But this is real simple. This is your sort of grid tie inverter with no battery. The only source is the array. And in this case, we haven't required any string overcurrent protection. So no problem at all. Smiling. But let's add another string. Okay. So we add another string of modules here. So we've got 3 strings in parallel, and I wonder what's going to happen now, because that means we've got 2 good strings feeding into a faulty string. And by the way, the faulty string doesn't work at all because it's basically overpowered by the higher voltage of the other 2 parallel strings. So we've now got another source of current. Okay, so we've got another 15.85 amps. And so that's a total of just under 32 amps. Just under 32 amps. Is it greater than the series fuse rating? What do you know? It's not. So even though I've got 2 good strings backfeeding into a faulty string, the faulty string can still withstand 35 amps in either direction, forward or reverse. So, in this case, and this is just to kind of prove that it's not a simple rule of once you get to 3 strings, you've got to have overcurrent protection. It's all about the ratio of n-1, the ISC of the module. N being -1 being the faulty string is the -1 times the number of strings times the short circuit current of the module. So we're all good at this point. All right, let's just kind of push our design one more step. And I think you can see where I'm going with this. And so I'm adding a 4th string. As soon as I add a 4th string, what do you reckon? Have we got a problem, Houston? Yep, we have a problem, because we've now got another source and another 15.85 amps, and we're well over the 35 amp series fuse rating that this string is having to absorb. So there you go. At this point, we definitely have, as I like to say, triggered the requirement for string overcurrent protection, and that requires in all unearthed strings, and in a floating system that means, all unearthed poles, having to put string overcurrent protection on both the positive and the negative end of those strings. Yep. I can see someone saying the stream is a bit choppy. Yeah, really apologise for that. You can blame Elon for his Starlink service being a bit choppy, but actually it's probably the weather as well because it's raining. And like I say, the recording will be fine. So if you just give up, you can always come back and watch the recording once it's finished, and I'll upload a clean version. So there we go. We've now got string overcurrent protection on all strings on both the positive and the negative poles, and the wording in 5033 is close as practicable to the point of combining, so usually at the well-named combiner box, or sometimes built into the PCE itself. Some PCE have multiple inputs, and they actually have fusing arrangements internally as well. Now the next question really is, what value should those be? Now there's a range. You can go between 1.5 and 2.4 times the short circuit module rating, but my recommendation is go high as you can. So just go right up to 35 amps. And the reason for that is that you don't want false tripping. So if you go too low, you think you're kind of being safer, you're likely to get under higher radiance conditions, one of these strings, or even all of them, tripping out on you. So you lose them even though there's no fault. So go high, go to the series fuse rating. It is what they're designed for. And they call it a fuse, even though you can, the overcurrent protection rating says that can be a circuit breaker. In practice, a fuse is what you want to use. And so it needs to be a suitable fuse. And so there's a type of HRC fuse, which is designed for PV arrays. And it's got the sub-name GPV. So GPV is a category of fuses that have a relatively low overcurrent trip point and sort of designed for a 2-hour overload before they trip, which is typical of a PV array middle of the day. So go high, go to 35 amps in this case, and there you go. So we've now triggered the requirement for string overcurrent protection. So just going back to my slide here, a few definition of terms. So you'll see on this slide it's referring to, in fact, if I just go back a step, I just realised I jumped ahead here. This is the formula from 5033, and you'll see down here it was this strings. For strings connected in parallel, overcurrent protection shall be provided when, and there's a bunch of terminologies or notations. IF string, IBF total, and IMOD max OCPR. What on earth is IMOD max OCPR? Well, that's where this slide comes in to explain the notation requirements. So IBF total, total continuous backfeed current from all sources not originating from the PV modules. So in this case, the example I gave just here, there is no other sources other than the PV array. So if this was a grid tie inverter, it's considered a one-way device. It doesn't take AC, convert it to DC and supply that to the array. So the only sources are the array. But if you had batteries on the DC bus anywhere on the PV cable, or you've got a non-isolated charge controller, which means that maybe the positive or negative leg of the charge controller is directly connected to the battery, you've got another potential source of fault current, depending on which pole is faulty. So, IBF total doesn't apply in my example, but certainly when you add batteries and or DC storage on the PV array, which is a bit odd, but it does exist, then you've got to consider that as well. IF string is the potential fault current in a string from other parallel strings. So we just looked at that. Those extra 3 strings which can backfeed is the potential fault current. And IMOD max OCPR, it stands for PV module maximum overcurrent protection rating. So OCPR, overcurrent protection rating, and it's based on a test in the IEC standard for PV modules, IEC 61730-2 for silicon modules, and there's a different test for amorphous. But basically, the test involves running a test current for 2 hours through the module in reverse, and there should be no scorching of the tissue paper or muslin that they put on the front or back of the module over that period. So it's really a thermal test. So there you go. That's what the series fuse rating on data sheets for modules actually is. It's the OCPR based on IEC 61730. Cool. So how are we going? Now, for the international audience, I just thought I'd throw this one in here. Now, since I was in South Africa, I had a little peek at their national standard, which is based on the IEC standard, as you can see by the title up there, IEC 60364-7-712. Now, I'm not a South African standards expert, so there may be some slight variance, I don't know, but you can see the formula below from the South African standard is very similar. It's basically saying n-1, the number of parallel strings, times the short circuit maximum of a module. If that is greater than the series fuse rating, the IMOD max overcurrent protection rating, then you are required to have string overcurrent protection. So it's pretty clear in both the IEC standard and the Australian standard at which point you require to do this, to put in that string overcurrent protection like this. And it adds a lot of complexity. Now, why wouldn't you just do it anyway? Let's say you had 3 strings and you go, I don't really need it, but I might as well. It's sort of handy for a test point or whatever, like I can bring 1 string on at a time. You're totally at liberty to do that. You can put extra points of disconnection for whatever maintenance purposes you want, but I would advise against it. Every connection that you add to a DC path is another potential point of failure. Every screw terminal that you haven't tightened properly or has moisture ingress or even just condensing moisture is a potential source of failure. So only put it in if you really need it. And sometimes designers just try and avoid getting to this situation where they need it by using more MPPTs. So using an inverter that has more MPPTs, and you can keep the number of parallel strings below the threshold. So yeah, my advice is keep it simple, stupid, and avoid potential failure. So back to my slide. So here we go. This is the formula in 5033 for iString max. So what's the maximum current from a string? Now, it's a little bit more really than the 1.2 SC module as I just drew, because I didn't allow for the safety margin. So I probably should go back and throw that in there. So we've got to allow for the safety margin of 1.25. Okay. And the reason for that 1.25 is to allow for both derating of protection devices and also high irradiance and positive tolerance of modules. So modules often have a 0 to +5 tolerance range. So your panels might all have, by luck, 5%, or these days it's more like 3, but anyway, percent more current output under 1,000 watts per square meter, and under higher irradiance, because irradiance, certainly in the southern hemisphere, is often greater than the test irradiance of 1,000 watts per square meter. So if that's the case, you're going to get a higher current. So a current from a PV module is proportional to irradiance. So that's the safety margin, basically 25% safety margin over the test for ISC module. So going back to the formula in 5033, you'll notice it's got this Ki in there, Ki. So Ki is the bifaciality factor. And because the modules I chose here, these Genco Tiger Neos, the particular modules are bifacial. So they've got the back of the module can generate some current, and the front of the module generates a lot, hopefully. And so you've got to consider the bifaciality of a module. So Genco very kindly, and some data sheets are better than others. Whoops, gone the wrong way. Some data sheets are better than others, and this one actually puts in the BNPI. Wow, there's another acronym. Bifacial nameplate. What's it stand for now? I'm trying to remember. Bifacial nameplate irradiance, so BNPI. So the BNPI is given as a separate table. So you'll see that the standard test conditions, STC, say that that particularly 470 watt module has an ISC of 15.85 amps, which is what I used in my equations. But if it's installed in a manner that is not parallel to the roof, therefore and shading the back of the panel, it will have some bifacial extra boost, and that's when BNPI comes in. And BNPI is kind of like a rule of thumb. It's allowing for an extra 13.5% production. So in the case of a test standard of 1,000 watts at the front and 135 watts at the rear, you'll get 17.55 amps out of those bifacial panels. And that means my little diagram back here, if I were to install this system in a manner that the rear of the modules are exposed to the albedo, excuse me, a little burp there, the albedo of the Earth, which is the reflected light from anything, not direct or global, but reflected light, then this 1.25 times we also have to include the BNPI value. So that would mean no longer would I be considering the ISC as 15.85. I have to cross that out. and add it up to 17.55. But actually, the proper formula, which is shown, if I go back one, sorry I'm jumping around a bit, this is a little complicated, is you actually put in the Ki value. Now, how do you calculate the Ki value? I mean, in the case of Genco, they actually kind of give it to you, which is really nice. They give the BNPI for the module. But actually, if you go to Appendix J of 5033, there are 3 ways to calculate Ki. And let me just take you to that. Here we go. So Appendix J of 5033. Now, Ki for bifacial arrays shall be calculated in either of the following ways. So you're actually given 3 ways to do it, and I've highlighted some of the keys. So A is calculated by simulation. I think that's probably something that you would do for a solar farm project. Imagine having to simulate every small install. So I think A is unlikely, but it is probably the most accurate. And simulation doesn't actually mean you have to put the real modules up. You just need to have some simulation environment based on the design, and if you know what the albedo is going to be. It's a bit complicated. B is where simulation data are not available, Ki shall be equal to the ISC BNPI divided by ISC mod. So what is that? So the ISC BNPI of the modules that we looked at was, I've got to go and look it up again, is 17.55. So ISC BNPI equals 17.55, and we divide that by the ISC module, and that's 15.85. And I just realised I didn't do the sums beforehand, so I'm going to have to do it live. Whoa, whoa, whoa. That's a bit fun. Just see all my posts. Here we go. Okay. So 17.55 divided by 15.85 equals 1.1. If we round that up, 1.1 approximately. Okay, so that's our Ki factor. So what I really should do is multiply this again by 1.11, 1.11, etc. 1.11, and that's going to significantly change the I-string max of those examples there. So let's run that one through. So 15.85 times 1.25, the safety margin, times 1.11 Ki for bifaciality, means that I've got a whopping, let's just call it 22 amps, rounds it round. So I've got a whopping 22 amps. That's a hell of a lot more than my original 15.85, and I could see straight away that as soon as I have 2 strings, I can get rid of the third one. As soon as I've got 2 strings in as sources to the faulty one, I've got 44 amps. That's more than the series fuse rating. So that brings me back down to 3 strings. I definitely need string over current protection. So important to consider that Ki value as a result. So there you go. That's what bifaciality adds to an equation. So what about if you're using optimizers? Now, I've got another drawing here for optimizers, and it's different. It's different. So with optimizers, they are technically called DC conditioning units, or DCU, and they modify the voltage and current between the module and the string to which they connect. So, for instance, a popular brand like SolarEdge optimizers, or Tigo, or Huawei, all of them make optimizers, but they are proprietary in the way they work, though Tigo is a bit more generic. They'll work with any PCE, whereas SolarEdge only work with SolarEdge inverters. In fact, you have to use optimizers with SolarEdge because all of the MPPT function is actually in the optimizer. The the inverter itself is just power conversion. Whereas with Huawei, it's kind of either or. You can use partial deployment of their DCUs or full deployment. But yeah, check the manufacturer's specification. So in this case, the SolarEdge optimizer has on the data sheet, a string max. I should bring it up for you so you can see it. A maximum output current of 15 amps. And when you're calculating iString Max for strings that contain either partial DCUs or strings with DCUs in all modules, there is different formulas. So with SolarEdge, you are putting DCUs in all modules and therefore use C. So C tells you that iString Max is the maximum current of the DCU. In the case of SolarEdge, that's 15 amps. So there you go. Yeah, sorry, Tony. Apologies for the stuttering live, but it is being recorded locally, so I'll upload it. So you might have to watch it tomorrow without all the stuttering. It's just a bit of a drama with my primary internet wasn't available, so I'm on my backup at the moment. But that's what local recording's for. So, I mean, thanks, Tony, for turning up, and I'll have it fixed by next week. So, yeah, so for SolarEdge, which is a string, all modules have DCUs, it's 15 amps is iString Max. But if you're partially deploying, so in the case of Tigo and Huawei, it's possible to do partial deployment. That means some modules. In fact, I often say you can just put the Tigos, for instance, on the problem panels in a single string, and it helps with optimizing against shading. And if that's the case, you have to use either the greater of those two equations, either the IDCU string max or the previous equation for a module including KI and the 1.25 safety margin. So that would significantly change things. And just to show you with Tigo have been quite helpful here because they've looked at 5033 and given you a maximum current output based on the clauses in 5033/2021. And so they say that the maximum output current is whatever the module's maximum current is, so I mod max. Even though the maximum current of their Tigos is 15 amps, under fault conditions, I assume you could get the full current of the module. So there you go. iMod max is what Tigo state. Okay, how are we going there? It's quite a lot of tech, isn't it? So yeah, it adds a bit more complexity when you're doing DC conditioning units. And as I said before, some module manufacturers give you a BNPI, and in the case of this particular one I found, Sumec Phono Solar, they very kindly go as far as giving you the figures for different levels of albedo, so how much reflected light there is, 5%, 10, 15, 20, 25. Now, how do you know what the amount of reflected light is? Well, you can actually measure it. So I've got some test gear that I use, irradiance meters, so you could actually measure it. But what's the benefit? That's probably one of the key things about bifacial panels is you're sort of getting something for free. You're getting what's otherwise waste energy from bounced off the earth or neighbouring objects like roofs, etc. And here's a little example of what's a typical energy gain from a bifacial module. So we're getting something like 19% more output from white painted roof if you tilt your panels so that they can get reflected light. Wow. I mean, consider how much we fight to get 1% more efficiency out of a module by going to, tier 1 modules, and you can get 19% more out of that tier 1 module just by tilting it up and having a light coloured roof. Sand is quite reflective too, so say 9%. Cement depends on kind of how dark it is. Grass is pretty poor, and water's even worse. So you can get a little bit off grass. And in fact, I've measured it here, and we get about 8% off our solar trackers because they're well clear of the ground. They're a couple of meters off the ground. So off the grass, we get about 8% more production on it in average. So that's one of the benefits of bifaciality. Another benefit, in fact, I didn't even think about this one, is that you've got a slightly longer production because you'll get to the switch on voltage earlier in the day and stay on till later in the day. You do extend the production period a little bit. It's not a lot of kilowatt hours though, because it's really at the tail end of the day. It does depend on whether it's a fixed array or a tracking array. A tracking array will have a much flatter curve and therefore potentially a bigger benefit from that bifaciality. And there's a test array that we have in the foreground and some trackers in the background here at the Smart Energy Lab. The test arrays are just being built out at the moment. Those are for a company called P-Vision. They've got sites around the world. I'm one of their 5 sites. I'm the cold climate site, I think. And we're measuring all of the factors, albedo, UV, global solar radiation, incline solar radiation, a whole bunch of things. So it's pretty cool. And where did I go next? So that's just a reminder that depending on the amount of albedo, your values for a module can be significantly greater, both in current and in power. Now, I've got to give a big plug to GSES. GSES produced some really great training and also some really good tech info on their website. So there's the link to their website, and there's the in-depth article on exactly what we've been talking about, PV overcurrent protection. In fact, they wrote this showing what the changes were from the 2014 edition to the 2021 edition. So, big cool shout out to GSCS and my friend Jeff Stapleton, who founded the company decades ago. Jeff's a bit of a legend globally. So there you go. That's string overcurrent protection in a nutshell. Okay, now that's kind of what my key messages for today was, and this might not be the full hour session, but I just thought I'd run that all past you and see if we can come up to speed. It was kind of funny when I was in South Africa. This was actually a really hot topic, and shout out to Tinas. G'day, Tinas. Jokingly referred to as the fuse police. We had quite a I wouldn't say heated, but back and forth during the presentation about whether you needed string overcurrent protection or not. And I think Tinnis's approach was certainly very aware of the challenges when it comes to other sources of current, particularly batteries. But I was kind of trying to argue that in a system without other DC sources other than the PV array, for strings of 2, definitely never need it. It's only when you get to 3 you got to start doing the calculations. So there you go. It's it was a little bit of a hot topic in South Africa. So please feel free to reach out to me and ask questions. Every week I get a few good ones come in via email, so I'll just put my email address in there for anyone who's new. And hang on, just typing it in there. There you go. And any ideas for future Toolbox Tech Talk. So I try to make it relevant to what you're involved with and any challenges. So there you go. Feel free to reach out to me and suggest some topics or ask further follow-up questions from this Toolbox Tech Talk. So the next Toolbox Tech Talk is Sunday, the 23rd of February at 1 p.m. Australian Eastern Daylight Saving Time. I'll be there and looking forward to seeing you. So that's it for today. Thanks for everyone for watching.
Wife, you know you're begging for my notice. Promise you're the same. Running for the meds. Sure you like my vibe. I smell candy on my wrist.